homework was that show that PK is bounded above by 2 over A, right?
You can string.
Yeah. So, right.
I wrote PK. It's fine. Both will work.
Yeah.
PK and PK.
So this will actually give a bound on pi x, which we are going to see soon, and we'll try to weight that. And so this will give, have some implication about pi x. Okay. And what else? We also talked about some polynomials which produces primes. And well, not all of them. So there were some homeworks about the polynomials which produces primes. We asked you to show that there doesn't exist a single variable polynomial which produces a prime for every integer inputs or a multivariate polynomial. Actually, the single variable case, as you've done, so actually that solves the multivariate case because you can restrict the other things to some particular values. Then you are getting a single variable polynomial, and if you get a contradiction for that, then you get a contradiction for the entire thing. And then there was this theorem by Jones, Atowada, and Wins that there exist polynomials whose positive values for positivity inputs are giving you all the set of the entire set of primes. And then the challenge was to bring both the variables, the number of variables, and the number of the degree of the polynomial down. So we'll talk about it a little bit more, and we must also talk about this polynomial. Is consider this one. So this polynomial actually produces primes for the values, or produces its prime outputs for all x in 0, 1, 39. Okay. And if you consider instead this polynomial, say plus 41, so instead of x, you're just taking x minus 40. Okay. Then this is primes for x in and for all x in 0, 1, 2, 7. The question is then whether there exist always polynomials such that given any k, it will take the prime values for 0, 1, or up to k. So there is a nice answer to it by Green and Tao in 2004. They proved it, and 2006 actually they got a principle for this. So it was a theorem on arbitrary long arithmetic progressions in primes. So you don't have to go to quadratic polynomials. You can do that with linear polynomials instead. So what does Green and Tao say? That there exists arbitrarily long arithmetic progressions in the primes. So in particular, if an arithmetic progression is of this form, a plus bx, you can put the values, so you can, what does it mean? That you can find an arithmetic progression, all of whose entries are primes. So take your first thing A as a plus prime, and D, the common difference with the next prime. So then this will yield the prime values for x up to the x going from 0 to up to the length of the arithmetic progression that you take.
Arbitrary long this
Arithmetic progression. So arbitrary long. So that means you have a polynomial like this, and for all the x's between some range like this, all the values are prime.
That doesn't necessarily start from 0, right?
No, but you can choose the first prime to be your first term.
Oh.
And then the difference with the next prime as your common difference.
So we can start from any prime and then find.
Not any prime. I mean, it just assures that there exist arbitrary long arithmetic portions in prime. So you are given k, you can find such a arithmetic progression there. And once you have such an arithmetic progression, you have the answer to the question that we asked. That is, whether such a thing is always true for any value, I mean, like 39, 79 there, for any given values. Whether there exists such a polynomial. So here's the answer by integer. Nevertheless, if we come back to the quadratic polynomial, even this is an open question. So there is a conjecture that there exists infinitely many primes of the form x square plus 1. It's not known yet. It's such a simple thing to state, but nonetheless we do not know how to do this. So there are some results by Ivanich about which are saying that there are infinitely many P2 numbers. P2 means that which are a product of at most 2 primes and which are of this form.
The prime can be visible.
Yes, these two P1 and P2. I mean the prime numbers. Now, if we think about the theorem by Jones and Watkins that we stated last time, we saw that the challenge was bringing the number of variables. So we had at least like variables and recall. So it was like, can this go down to 2? And the degree also. Well, have you also tried with why 1 is not possible? You can connect it with the thing that you have already proved. Okay, so try it next. Try that one. That is why the degree cannot be brought down to 1, such that all the positive values of the polynomial are primes. It is related with what you have done. The first homework. Well, the first homework was this one, the second homework. And here, won't it be nice if both of these could be brought down to 2? So this is 2. Well, it's given boxes, so we can just add it. Also, the case that it's an integer. And let n be some number in one. Then you write m as some n squared times s squared. The GCD of n and s is 1 and s is square. That is, all the prime factors of s are dividing it up to power 1. It doesn't have any squares dividing it. check what are the possibilities for this and this. Suppose the number of primes which are less than x is again, but we have not written it down here, but suppose it's pk. So suppose it's p1 or pk are the primes which are less than. And then this n is in this interval. So the factors of m are necessarily divisible by these primes of m. Let's figure out how many possibilities are there for s then. Number of possibilities for this. How many could be there? At most, well, P1 can divide S, P1 may not divide S. Two possibilities for P1, for the same and P2. The same possibilities for P2 and so on up to Pk. So this is an upper bound for the possibilities of S. At most two power k possibilities, right? And this was a square. We are not considering, not considering the prime factors of this, but just saying that this is some square less than x. Okay? So the number of possibilities for n is at most root x. Is less than equal. This is also less than equal to for k, and this is less than or equal to root x. So the number of possibilities for m then is less than or equal to 2 or 3 times 2 x or 3 times 2x. But note that we would have chosen m from in this interval, right? So actually there are x possibilities for this. Okay. So that implies x is less than or equal to or k 2x. What do we get from here? X is less than equal to 2 power 2k, right? Square both sides and cancelling x. So remember, this pk was the highest prime less than k. So you already got this. Earlier we had 2 power k and now it's brought up to 2 power 2k. So here we are using that log factor. So now that will imply this one will imply that if you take log x here, on the left hand side you are getting log 2. So that implies actually, I'm not sure whether this is coming in the range of the camera. So
there is also the upper bound of EK, not only pi.
yes, right. It's earlier we had to go to power k. Now this is already improved. And yeah, so right here you see that it is 4 power k. And this we are going to see again in a few minutes, that 4 power k. So look here now, it is k is larger than or equal to log x by 2 log 2. But what was k? K was the number of primes less than x.
Yeah.
which is pi x. Larger than log x. Log. And we did the entire argument with assuming x is an integer. The same argument holds if you work with any x but replace this one just with the floor of x.
Do you need the floor? If you just carry forward the argument taking less than equal to x, like considering the integer less than equal to x.
Yeah, sure.
Then
Let's check. So this one, I mean here less than equal to root x, it's still fine. Here to power k, it's still fine. And there we have possibilities for m. So this is still works. But here you will get box x.
oh.
So for in general, we have that pi x is larger than, okay, sorry, here. From this, when x is not empty. Alright, we said that we are going to see the same argument in proving summation one might be divergence. It's also proved by Ernst. So let's now consider that one. And it's proved by contradiction. So assume that, so now we are proving that summation 1 by 3 divergence. So divergence. Here's the proof. Assume converge. Yeah.
So in the proof of this, here we wrote n equal to n square times x where x is square free.
Right.
Then what is the guarantee that n and s are co-prime?
Okay, we assume that.
We are choosing n that satisfies this, that n and s are co-prime.
Right. Yeah, because you see here, well, anything. Oh, wait a minute. We did not assume that, and at first, I mean, suppose so. This was a bad assumption. Very sorry. Thank you for pointing this out. Because at first we don't require this, and secondly, suppose there is a cube. Then what we do? We put the square part here and take p outside here. So the possibility for this is considering this root 2k, whereas the possibility for this is considering the root x part. Thanks a lot for pointing this out. Now, assume this one converges. Then suppose these primes are enumerated by some p1, p2, as we do. So that would imply the tail part goes to 0, right? And that would imply that there exists some j, right, j0 such that the sum over j, these are the primes inverted, say p lines, I larger than equal to j0, this is less than half. Because the tail part goes to 0, so you will always have some integer, so that if you take the prime indices larger than that and sum the reciprocals, you get the rest of the tail of the series is bounded about by half. And there we are going to do kind of a similar thing with a similar estimate. So let again we are considering this picture. We are assuming that x is some integer, and these are the primes below x. Well, up to where we have said here I may be strictly greater than 0. Okay. So here, or maybe strictly greater than k. Excuse me. Because we don't have to change the picture then. Instead of J0, I just wrote k. And then we are writing, we are considering the things here, and we are breaking it exactly in a similar part, n squared and s. And then for n by n x squared denoting the elements, the integers in 1, 2, x, which are not divisible by any prime larger than x. That is any prime larger than pk. Just because the highest prime is in x. So now let's get some estimate for the size of mx. In fact, if you write the things in this interval, like the integers in this form, well, you get these estimates again. That is, 2 power k is a number of elements for number of choices for s, and root x is the number of choices for n. So number of elements for mx, I mean this 2k root x now would be an upper bound for the size of mx. So that will imply the size of mx, or you can also write the number of elements in mx is bounded above by this number. And now what we are going to construct, we are going to construct a lower bound for x. Let's write down something here, this estimate, so that we don't forget factors of pk. Till now we have obtained that it is less than 4. That was our weighted bound. And we said that we'll come back to 4 sometime. So this is our upper bound, and what we do now? We construct the lower bound, and how we cross it? So we consider this. That is the number of, well, we are now trying to estimate the number of elements in x which doesn't belong to mx. That is the number of elements which are divisible by the primes which are larger than x. So for each of these sets, say if the pi prime divides that number, let's denote by n1 x, and we write that n(x) is the numbers, the integers, the number of integers. We can also write it as a set, the set of integers. pi as needed as one of the vectors, or which it is a vector. So, can you tell me what could be an upper bound for the size of NIX? X was this, this is a set of integers in this interval from 1 to x, such that this is reducible by pi. So, the number of elements in NIX is bounded above by
X over pi
great.
lower of that.
So we can just write x over pi.
Yes.
Now, note one thing, that this set 1 x minus mx, that is a complement of mx in this one, is just the union of this nix, right? Where I is running from k to infinity. Right? So if you now estimate these ones, that is the size of this, you will get that this is x minus number of elements in mx, right? And that would be less than equal to the number of elements in this, which is less than equal to the sum over each of these ones. Okay? So we should seems to already get the argument. This is x by I. Well, first let's just write it down. This x I running from into infinity, and this is less than or equal to, well, strictly less than, because actually for pi's larger than x, it is not x by pi, but it is 0. So it should be strictly less than this one, x by pi, I running from a to infinity.
Pi larger than
X.
X.
Pi is at a prime, right? The I prime is pi. And then we have that this is less than x times, well, x times 1 summation over 1 by pi. I add from k to infinity, and that way it is less than half. Right? So it is less than x by 2. So we have x minus the number of elements in Mx is less than or equal to x by 2. That implies,
X over 2.
so if you take elements on the other side, you get that number of elements in Mx is larger than x by 2 from the last estimate. Now comparing these two, we get, hence, we have x by 2 less than 2k 2x, which is clearly impossible if x is large enough. So that is x, well, just 2x less than 2 over k plus 1. And what was k? K was that this was bounded above by half. And if it converges, there exists such a k, such a fixed k, that you can take k to the minimum number for which this happens. And then you are so you can choose x as large as you wish, and then you get a contradiction to this one.
This is for all. this is for all x.
It's for all x. So it's alright. Now let's come back to this one. We'll try to better this one, but this time, we are going to get the right hand side as this one. The left hand side we can improve much better than this. So,
Okay. Can you just once recap the entire proof?
the idea of the proof?
Yeah.
Yeah, sure. So we are assuming at first that it converges, and we are proving by conversion. So if it converges, the tail part goes to 0. And if the tail part goes to 0, that means if you take this indices high enough, then this will bound out by half. So take k with a minimum number for which this is applicable. Because if you take k large enough, this will be smaller than any given epsilon. So, and once you have this k, then you can list the primes. You want me to take pk and choose some x which is larger than that. Choose any x which is larger than that.
We are taking from P1 to PK.
Yes.
This
many tracks, and then your x could be anything larger than that. So now we are considering the set of numbers in 1 to x which are not divisible by any of the primes which are larger than this. Well, it was from I larger than I. So this will be, this will be this one.
Oh.
And this will be this one as well, because it's the primes which are larger than
The union.
Union. Yes.
So then that mx is count the upper bound of mx is obtained by the previous.
Right.
Yes.
Yes. That was the previous argument already gave us this one.
Yes.
So it was only about the lower bound, and for the lower bound we actually counted its complement, estimated its complement in this manner. So we defined by K9x the sets which are divisible by each of the number sets which are divisible by pi.
Yes.
And we are considering only the numbers between 1 to x. So this number, as I already mentioned, this is bounded above by x by pi. And we are just putting in there, and here this strict limit is there because not only, x by pi is larger than these things, even when larger than most of them, even when this pi is smaller than x, but nevertheless when pi is larger than x, then all of these things should be 0. And this here you are getting some non-zero thing. So there will be a strict limit here, and this is giving you that this one would be larger than x minus x by 2 on this side. So you are getting a lower bound. When you compare lower bound with the upper bound, and see that x will necessarily be bounded above by this. K was fixed, so this is the contradiction. Now, another thing. Maybe which part? Maybe this one can be open, first one. So here's the next thing is also, the proof we are going to give of the fact is given. Product over P is equal to K is bounded above. And the argument that we are going to give is, I think, also declared. It's a beautiful commentary argument.
Chebyshev one, there was a result of Chebyshev, was that related to this one?
Yes, yes, of
The
course.
binomial.
Yeah. x plus will prove Chebyshev's estimates. That is pi x will, we have, yeah, this is the best estimate for pi x that we have got in today's class. In the next class we will get even better estimates of pi x.
And also upper bound.
Yes, also. And that is the Chebyshev's theorem. That is pi x is bounded above by some bx by log x and bounded below by some bx by log x. And a and b you can take actually as close as possible to 1. And actually, prime number theorem is just that pi x is of the size x by log x. So that means that if you are taking the ratio pi x divided by x by log x divided by log x and letting x go to infinity, this ratio is going to 1. So in other words, Chebyshev's estimate is of the right order, but nevertheless, since if he has considered some constants here and constant there, and well, the fact that you can take the constants as close as possible to 1 is, well, his original argument gave some explicit constants a and b, but prime number theorem is a little bit more than that. Not a little bit, it's much better estimate. So yeah, let's come back to this one. The proof of this is by induction. And how should we proceed? At first observe that if k is equal to 1, you are just having 2. 2 is less than 4. If k is equal to 2, you are getting 2 and 3. 2 times 3 is 6, which is less than 16. So for 1 and 2, I can for k not 2, it's alright. So we got the result. The claim holds. Let the claim hold for some m. Well, also note one thing that the claim hold for some m. Some m larger than or equal to 2. Now note one thing, that is the product of the primes which are less than or equal to some even number 2m, to r, because we are going to use empty factors, so r. So the product of the primes which are less than or equal to r is equal to the product of the primes which are less than or equal to 2r minus 1 for all r larger than or equal to 2. That is, it suffices to consider only this product where k is odd. Now note one thing, that is the product of the primes which are lying between m plus 1 and 2m plus 1. This divides 2m to z. Why? Just write it down explicitly and you will see why. Plus 1 then 2m plus 1 is, sorry, so this is 2m plus 1 factorial by
Let's use m plus 1 so that you.
yeah, right, m plus 1 or m 2 right. So these primes are, these primes are only present in the numerator but not in the denominator. So that's why this will divide this thing. So note that this is, we just wrote it there, right? So 2n plus 1, choose n. This was the same. And both of these appears in the expansion of 1 plus 1 full power 2n plus 1. So this one is larger than equal to then 2n plus 1 choose n plus 1 and twice of that because this were equal. That implies that when choose n plus 1 is bounded above by this one is bounded above by 2 power n. That is 4 power n. And now the rest of the proof is just induction. So consider the product of the primes p less than or equal to 2n plus 1, and that is product of the primes p less than or equal to n plus 1 p times the product that we are considering product over n plus 1 less than p less than equal to 2n plus 1 less than p. And by induction, we may assume that this is this is less than equal to 4 power n plus 1. Well, here we can actually assume that the claim is true for some n plus 1. This here we are using induction. You see, so instead of having the induction plus for n, we just have it for n plus 1.
That is 2 to the power 2.
2 to the power?
That's
2 to the power 2. Thank you. So this is 4n plus 1 times 4n. So we are done. In fact, here actually we could make it a little bit better. This is a strict inequality because for 1 and 2 it was strict. And here the induction hypothesis could also be strict. In fact, here we can also have
The binomial.
right. So wait a minute. Yeah, we are assuming that a plus 1 is larger than 2. So this will also have. So indeed we have that this the product of the primes which is less than equal to n plus 1 is bounded above by 4 plus 1. Well, we obtain this, but note that it's we are only multiplying the primes which are less than equal to k. Earlier the estimate was
Only one.
pk is 4k, right? And this pk is not necessarily less than, it's not actually